Hello, yo, welcome back. All right, so we're going to continue from where we stopped. Now we are going to be discussing electric field. Okay, I'm very sure that you understand the meaning of force field. Now, what is electric field? Electric field is a region in the space where electric force is being experienced. Now, this electric force is experienced around that region due to the presence of an electric charge. As you can see, this is a positive charge and this right here is a negative charge. All right, located somewhere in the space. Now around this region, the region around this charge, lies a force, and the only way you're going to investigate the presence of this force, though the force cannot be seen, okay, it's a field force. It's not like it's not a contact force. If you bring another charge close to this region, that charge will experience a force of either attraction or repulsion depending on the polarity of the charge that you bring close. So around this region, all right, is a force, all right, and this are around this region are force, okay, which can be, of course, forces as a matter of fact, all right, which can be represented by a line. This line you see here uh, is imaginary line that is used to indicate the direction of the electric force acting in this region. And this imaginary line is what we refer to as electric line of force. So this imaginary line that is used to indicate the direction of electric force is what is known as the electric line of force. Okay, so for a positive charge, as you can see, the line of force is at always, the arrow is always pointing outward. So any place you see electric positive charge, one single line of force, the direction of the one single line of force is always outward. It's pointing away from the positive charge. Take note of that. All right. So this is electric line of force for an isolated positive charge. Isolated positive charge simply means that the positive charge is on its own, is not close to another charge. Now here is the one for an isolated negative charge. So as you can note, you notice the difference between the line of force of an isolated positive charge to that of negative charge is the fact that for a negative charge, the arrow is pointing inward. So please take note of this. Okay. So now, a situation where the two charges are brought close to each other, positive and negative charge, two unlike charge, okay? We call that two unlike charges, okay? So now, the line of force goes this way. It will always move from the positive to the negative. So this is how you draw it. Don't forget that, okay? It's always okay, it's always moving. The arrow is always from the positive to the negative. This is one of them is negative. Okay, so let me correct that. So this is the negative charge. Okay, all right, so these are two unlike charges. Now as you can see from this uh particular diagram, all right, this actually confirms Coulomb's law of electrostatic force, or okay, it confirms one of the law of electric force, which actually states that um, unlike charges attract while like charges repel. So this force that exists between these two unlike charges is that of attraction. So the line of force emanates from the positive charge, and actually terminates at the negative charge. All right. Now, if the two charges are two like charges, then you know what you're going to expect. You will definitely expect a force of repulsion. For example, two positive charges. So in that case, the arrow, all right, or the line of of force will always curve away from the other charge, indicating that there's a force of repulsion. So if you want to draw that, so this is exactly what you're going to do. So this curvature indicates that repulsion is existing. And don't forget that for a positive charge, the arrow is always pointing outward. While in the case of a negative charge, even though that the force is still repulsion, okay, don't forget the direction of the arrow. The arrow is always, okay, the arrow will point inward. All right, so okay, so just indicate that. Let me just draw as much as I could. All right, so these are two like charges. Okay, see the difference between the two unlike charges and two like charges. Okay, all right, so now let's now get to the formula part. Okay, so now there's one thing you should actually take note of. As you can see, this line of force can be as many, okay, can be as many line as possible. Then what you should actually notice about electric line of force is the fact that okay, the number of lines depend on a quantity known as electric flux. Okay, so in this area, in this unit area, okay, the number of line, so electric flux, okay, is the total number of line of force. All right, in this that is actually measured in this unit area, or in the specific, in that specified region where the electrical force is being experienced. So now the number of lines of force per unit area depend on the strength of the charge. Okay, the higher the strength of the charge, the more the number of line of force. So the number of line of force, okay, that is measured in an electric field depend on the strength of the electric charge or charges found in that particular region. So that will now bring us to what is referred to as electric field strength. Okay, so we are going to talk about electric field strength or electric field intensity. Okay, and by the way, the symbol for flux, electric flux. Okay, of course, we use the symbol phi. All right, and electric force is approximately electric flux in an electric field. Okay, by the symbol phi is approximately equal to the magnitude of the electric charge. Okay, so the magnitude of electric charge, this is an electric charge, the amount of flux that's okay, that that is measured around this electric charge is approximately equal to the magnitude of the electric charge. So that is why in electric field, electric flux, all right, electric force is measured in coulombs. Don't forget that. All right, so let's now get to what we are to discuss: electric field strength or intensity, or electric field intensity. All right, so by the symbol E, electric field intensity is defined as the force experienced by a unit charge in an electric field. Force per unit charge. Okay, let me use small letter q. All right, force per unit charge. So this is one formula for electric field intensity, and the unit from what we have here, the unit of force is Newton and the unit of charge is Coulomb. So this is Newton per Coulomb. This is one formula for electric field intensity. So please take note of that. All right, then we can also express the formula in terms of force. We know that force is equal to, as a matter of fact, K Q1 Q2. Since we are dealing with just Q, I'll just say Q times Q, which of course is Q squared. Let's say the charges are of the same magnitude, okay? Q1 Q2, that is Q times Q, which is Q squared. You know this already, of course, divided by R squared. Okay, so this is for the force. The whole of this is for force, of course, divided by charge per unit charge. All right, so I'm dividing this by a unit charge. So as you can see, Q square divide Q. If I just cancel this, Q square divided by Q, I will just have Q. So that means electric field intensity can be expressed also as okay, also can be expressed as KQ R square. KQ R square. So please take note of this. So it's either, let me call this formula number 1. This is formula number 2. All right, it's either we use this or we use this. Okay, I hope that is well understood. Then of course, there's another formula which of electric field, which of course I will still introduce it. Now let's look at what is known as flux density. Okay, electric flux density. The density of electric flux. Okay, all right, so the density of electric flux, the symbol is D. All right, is always equal to the electric flux per unit area. And we know that approximately electric flux is equal to the quantity of charge, then of course divided by area. Okay, so now the relationship that exists between electric field and electric flux density. Okay, electric field is equal to the electric flux density divided by the permittivity of that particular medium where the electric field is being measured. And of course, you know that the symbol epsilon is permittivity. Okay, so the electric field intensity is always equal to electric flux density divided by the permittivity. So please take note of this. So this is another formula, all right, of electric field. So this is the formula that relates, this formula actually relates electric field with electric flux density. And you know that, of course, this is permittivity. If it is free space, if we are measuring this, the electric field in a free space where there is no medium, okay, or possibly, let's say, you know, we usually, air is actually approximate, please pardon me, air is approximated as a free space because its relative permittivity is always 1, okay. So let's say this is a free space or air, all right, then we can write the electric field intensity as electric flux density, then divided by epsilon zero. This epsilon zero is permittivity of free space or absolute permittivity. So call it permittivity of free space. But if it actually happens that the medium where this electric field is being measured is not in a free space, let's say it is inside oil. It's not just air, that's oil is filled in that particular region where the electric field is being measured. All right, then what we are measuring, what you're going to measure inside this is not going to be permittivity of free space. Okay, we measure the actual permittivity, and the actual permittivity of other materials except air, all right, which is permittivity, is given as relative permittivity, which of course is a constant for different material. Oil has its own, paper has its own. Okay, every material have their relative permittivity, then multiply by the absolute permittivity or permittivity of free space. So this is the relationship. Okay, this is the formula you're going to use to calculate the permittivity of any medium that is not free space. All right, so all you just need to do, let's say for example, it's a material, it's a medium whose relative permittivity is 2.5. Okay, so for you to calculate the actual permittivity of that medium, all you just need to do is to multiply the relative permittivity 2.5 of that particular material, all right, which will be given, then times the permittivity of free space, which of course you know that is 8.85 times 10 raised to the power of minus 12. Okay, all right, so please take note of that. This is just for illustration's sake. So that way now we can also have it that electric field in terms of electric flux density is can be given as electric flux density, then of course divided by for other medium. Okay, this is for other medium, okay, except free space. Okay, E is gonna be D, then of course multiplied by the permittivity, which is given as relative permittivity times absolute permittivity. All right, so these formulas are really very important, so you should take note of them. All right, so let's just let's work on example. Right, I've given you some formula, but we need to solve some question. Okay, so now the question is we're asked to calculate the electric field at a point which a distance with a distance of 5 cm from a charge Q of 6 microcoulombs. All right, so solution. If you have been given such a question, what I did was I just wrote the parameters. Okay, of course I'm going to be bringing questions in the next video. We're going to solve a lot of questions, but for me to illustrate the formula so far, I need to just give you something, right, so that we can use it to illustrate. Okay, so here we go. Now, as you can see, in this case, we are to calculate the electric field, and the distance from the charge where we are calculating the electric field has been given. All right, and this is a positive charge. Okay, so in that case, the formula of electric field we are going to use is the one that has distance, which is given as KQ all over R square, if you can still remember. Okay, so that way now we have it that electric field intensity is going to be K, a constant value, 9 times 10 raised to the power of 9, multiplied by Q, which of course is 6 microcoulomb. So you have to convert that to coulomb by multiplying by 10 raised to the power minus 6, then divided by the 5 cm, which of course is our distance, the distance. Okay, we are calculating the electric field intensity, and it is 5 cm. I have to convert that to meter, so that's going to be 0.6 0.05, if I'm not mistaken, meter, then squared. Okay, so here we go. We could just calculate this. Okay, so 9 times 6, that should be 54 if I'm not mistaken. Yes, okay, 54. Then of course multiply by 10 raised to the power 9 times 10 raised to the power minus 6. That will be 9 minus 6. Okay, and the power will be 9 minus 6, which of course is 10 raised to the power of 3. Then this right here is 5 squared. This is the same as okay, let me divide that. Okay, this is the same as evaluating 0.0, okay, 0.05 square. So the same as evaluating 5 times 10 raised to the power minus 2 all square. This is what it means. So here we go. This is going to be 54 divided by, of course, 5 square is 25. Okay, so times, for the powers of 10, this 10 raised to the power of 3 divided by 10 raised to the power of minus 2 times 2 minus 4. Okay, so you can use your calculator to evaluate that, and you are good to go. Okay, so let me just get a calculator so that we have the answer. All right, so here we go. This is 54, then divided by 25. Okay, so 2.16. The electric field is for this number. All right, 2.16. Then for the powers of 10, you know what is going to happen. So if you take this up, that will be 10 raised to the power 4. 10 raised to the power 3 times 10 raised to the power 4 will give us 10 raised to the power 7. Okay, and the SI unit is Newton per coulombs. Okay, so that is another formula which also I'm going to show you. Okay, another formula for electric field intensity. All right, but before then, don't forget that it's either it's Newton coulombs or it is volt per meter. Now the origin of this unit, volt per meter, is what I'm going to show you later. That is the when we discuss the relationship between electric field intensity and electric potential V. Okay, so the relationship that exists between these two, that's when you get to know that electric field intensity is also measured in volt per meter. All right, so that is it for this video. We're going to look at more in the next video. So see you in the next video. Thank you very much.